Ahead of several future projects, I wanted to create this tutorial on how to use various types of encoders, specifically single-phase encoders and quadrature encoders, using both optical sensors and Hall effect sensors. A lot of the great tutorials that I've seen online take a theoretical approach to how encoders work, going through all the pulses and determining the direction of rotation and so forth. And I'll definitely touch on all those things, but I also want to give a practical demonstration as well as an explanation of the software and how it'll work to actually read this sensor so that it can be scaled to any arbitrary type of encoder. These are the three encoders that I have on hand, and I'll be using them to demonstrate various aspects of encoders. At its simplest form, an encoder is an electromechanical measurement device that gives information about the angular position of the rotating axis. So, as you can see, it's a disc that spins around, and then there's going to be some sensors that we'll come to in a second, and those sensors are going to give information about the position of this and the rotation. Over here, so this one is just a single phase encoder. This one instead is going to be a quadrature encoder. And as you can see, it's the same principle as the previous motor and encoder. It's a DC motor with a gearbox axle coming out. This one's interesting in that the rod extends out both ends. So you can see it comes out here, so it'll be spinning both ways. And then this is the encoder circuit. And it's a little hard to focus in on, but these two chips here are Hall effect sensors, and so they're going to detect changes in the magnetic field, specifically the magnetic field of this disc as it spins around. And so I will come back to all of this and explain it in more detail. I just kind of want to give you a brief overview of the different types we have here. Finally, there's this one. It's a quadrature encoder, so similar to this one, it's got two sensors 90 degrees out of phase to each other, except instead of using magnets, this one is again like this, an optical encoder. So we'll start off here and then kind of build up and touch on all these other ones. If you want to jump to a specific type of encoder and see how to use it, see the software and so forth, I'll put timestamps in the description down below so you can jump around the video a bit. One quick point to clarify is that encoders don't necessarily need to be attached to motors. These two obviously are attached to a motor, and the reason for that is just that you can get information about the RPM of the motor, which would be useful if you want to determine the speed at which the wheel's spinning and so forth. But in other applications, you may not want the encoder directly attached to the motor. You could have this on a free spinning axle or something, and that's where this encoder would come in. So yeah, while it does look like there may be a motor and a gearbox in there, there's nothing in there. It's just a free spinning axle here, and this entire piece is the encoder. So to begin our exploration of encoders, I'm going to start off with this simple entry-level encoder. As I mentioned, this is just an optical disc, and what I've built here is a small circuit. So this white, or rather clear LED over here, it's a little hard to see, but it's just above the tip of my finger, is an infrared LED, so that emits infrared light. So as humans, we can't see that, but it is sending out light. And then this black, it looks like an LED too, is an infrared receiver. So basically, if this is turned on and there's nothing blocking it, then this infrared receiver will read a state of high. If something's blocking it, say my finger, then no infrared light is getting to this receiver and it will be read in a state of low. So basically I've connected it up to an Arduino here, and then the output of the receiver is connected up to digital pin 2, which is an interrupt pin on the Arduino. If you're familiar with what that is, that's great. If not, I'll come back to that in a second. But it's important that this is connected to either pin 2 or pin 3 on the Arduino Uno. So I've gone ahead and powered up the board, and as I mentioned before, as a human we can't actually see the infrared light that's coming out of here, and neither can we see it through the lens of my camera. Even if I make it darker in there, you still won't see any infrared light coming out of that LED, and that's because there's an infrared filter built into the camera. My phone, while it might have an infrared filter, it definitely isn't as great, and so if I line this all up correctly, you can see, especially if I make it darker, you can see the infrared light coming out of that emitter there. So by positioning the optical encoder in between the infrared emitter and receiver, essentially as this rotates around, either light's going to be allowed through when there is a slot, or it's going to be blocked when there's a piece of solid acrylic. So I have my power supply over here. I'm going to use that just to connect up to the motor. And when I go ahead and turn it on, just move that off to the side for now. So this is definitely a bit of a sketchy setup, but just kind of for demonstration purposes here. When I go ahead and power it up, and if we go take a look at the output received on the Arduino IDE, we can have a look at those pulses as they're coming through. You can see we get this nice clean square wave. Every time it's high, the light's shining through the slot, and then when it's low, the light's being blocked out. So I guess the question now is, how do we actually get this output onto the computer in the first place? So I'm going to dive into the short little program that I wrote for this. As you can see, it's not very long. At the start of the program, we're defining the pin that the encoder is attached to. In this case, it's digital pin 2. Like I said before, it either needs to be digital pin 2 or digital pin 3. The line that I'll bring your attention to is in the setup routine, specifically the attach interrupt command. If you're not familiar, interrupt commands are very useful when you're sampling a lot of data from a sensor very quickly, and you want to make sure that you don't miss any of the inputs. For example, further down in the program, you'll see that I'm printing out the value of the encoder. This is actually quite a slow process, and comparatively speaking takes a lot of time, and so if we were to execute that without doing anything else, then we'd actually be missing pulses as they came through on the infrared receiver. So what the interrupt routine does is it basically prioritizes the input from the sensor, and anytime the state changes, specifically when it's rising, going from a low state to a high state, it's going to prioritize the function called pulse, and this function is going to increase the count or the number of pulses that we've tracked. So now if I go ahead and comment out this line and uncomment this line, we'll see how the output changes. Specifically, we're no longer getting a square wave out, instead it's going to steadily rise upwards as the count increases, or the total number of pulses. Obviously, as you saw earlier, my setup for this experiment is a little precarious, so the output is unstable, but you'll see in the later part of this video we do get stable outputs when the encoder is properly installed. Now that we've finished discussing this simple hobby optical encoder, I wanted to move on to this other encoder mounted on a motor, except this time it's a quadrature magnetic encoder. So instead of having slots like in the optical encoder, this one has instead alternating magnetic domains in this black disc that spins around. If I go ahead and just pull this off the end, it's a little bit tight. Being magnetic, you'll notice that it catches onto the metal spine of my notebook. In order to see those magnetic domains, I'm just going to pour some iron filings on top of the magnet. So as you can see, the iron filings have moved to align with the magnetic field lines, and in the center here we have 6 distinct clusters of iron filings. So these are alternating north-south polarity domains, so every north pole here has a neighboring south pole on each side. By knowing that there are 6 domain changes in this disk, we can count the pulses sent from the magnetic sensor to the Arduino to figure out the RPM as well as the direction of rotation. In the corners, these 2 black surface mount devices are Hall effect sensors, and what they do is detect changes in the magnetic field, specifically the magnetic field of the disk as it's spinning around, and they'll send a signal out through these wires to the Arduino when they detect a change in the local magnetic field. These 2 sensors are out of phase by 90 degrees, and what that enables us to do is actually determine the direction of rotation of the disk as it's spinning, whether it's going clockwise or counterclockwise. This was something we couldn't do with the previous optical encoder because it only had one channel. We'll go have a look at the output of these two devices to see how we can determine the direction of rotation of the encoder. So just like in the previous example, the two outputs are square waves. Let's call one of the Hall effect sensors channel A and the other sensor channel B. You'll notice that because the sensors are out of phase by 90 degrees to each other, the outputs are also 90 degrees out of phase from each other. So how can we determine direction? Well, let's say, for arbitrary sake, we're traveling clockwise in this direction. By looking at the rising edge pulse of output A, so that's going to be every time that output A changes from a low state to a high state, so here, here, and here, and comparing it to what channel B is saying at that exact time, we can see that when it's going from low to high, output B is high. Same here, output B is high, and here, output B is high. Now what if instead we were traveling in the opposite direction? I'll indicate this with the green arrow. We still want to look at the output from when it goes from low to high, but because we're going in the opposite direction, it's actually going to be this rising edge here. And you can see that every time that channel A goes from low to high, output B is in a low state, output B is in a low state, output B is in a low state, and this is always going to happen. So by writing a program that looks for every time A transitions from low to high, and then checking whatever the state of B is, we can determine whether it's spinning clockwise, B will always be high, or if it's spinning anti-clockwise, B will always be low. Furthermore, just like before, by counting the number of pulses, we can determine the RPM and the total number of revolutions. The nice thing about having two outputs is that we get a higher resolution than before. So in this circuit, the motor is connected up to the motor driver, which is going to control the speed and direction of rotation. Then the two output signal lines from the two sensors are going to digital pins 3 and digital pins 2. The motor driver is controlled by these two signal lines from digital pin 10 and 11. And then finally there's logic level power going at 5 volts to the sensors on the motor. I've connected an external power supply to power the motor driver and by extension the motor itself, as it's never really a good idea to draw power directly from the Arduino. So when I go and upload this code and power it all on, here we can see the output from the two different channels as I drew previously. And you'll notice that they're out of phase by 90 degrees. So let's go into the software and see how we can change it to count the number of pulses as well as the direction of rotation. So overall, you'll notice that this code is fairly similar to the previous code that I demonstrated. We're defining the encoders, the motor, the counting, everything we've just kind of doubled up because this time we have two sensors instead. And here we're declaring the direction variable, and just for convention's sake I'm going to define one as being clockwise, -1 being counterclockwise. In the setup it's all pretty standard stuff, just declaring the pin modes. Like before, we're using the interrupt service routine on the rising pulses, so that's going from low to high on both of the encoder sensors, and that's going to run routines pulse A and pulse B, which are defined down the bottom here. Recall from earlier that we wanted to check what the output of B was when A was rising from low to high. Therefore, every time that we get a rising signal from pulse A, we're going to want to check the direction. The check direction function is fairly short, and what this is doing is basically comparing encoder B and seeing if that one's in a high state. As we said before, we know that it's spinning clockwise, so we're going to set the direction to 1, or clockwise. And then if encoder B isn't in a high state, it's obviously going to be in a low state, so we're going to say it's moving counterclockwise. But we're only going to be checking the direction when we call pulse A, because as I mentioned before, we just want to be checking what the output of B is when A is on a rising pulse. And lastly, we'll just increment the count of pulses by adding the direction. So if it's spinning clockwise, that's going to be 1, so we're going to be increasing higher and higher, and if the output is -1, then the count is going to be decreasing. So this is just an arbitrary convention that I've chosen for myself. And in here I just have a selection of different things that we may want to print out and see as a user. So in order to see those two square wave pulses, I was just using these two functions. If we want, we can go ahead and comment these out and uncomment these. Go ahead and upload this, and then we'll be able to see the output. So now when I go and power on the motor, we'll see that it's steadily declining, and that's because it's spinning anti-clockwise. If I take a second and pause here and redo the wiring and make it spin in the opposite direction, you'll see it's starting to climb back up. And obviously you can change the direction and the speed inside the software, but for these purposes I didn't really want to focus on that. And there you have it. Last but not least, we have this optical quadrature encoder, which is very similar to the previous magnetic quadrature encoder, except that it's not mounted to a motor and it's just a free spinning axle. Whereas this smaller quadrature encoder only had 6 pulses per revolution, this one actually has 1024 per revolution, so that gives it a much higher precisional accuracy. And one other nice feature is that in addition to having output A and output B, it has a third output Z. And output Z, it only sends a signal once per revolution, so most of the time it's just going to be continuously flat, and then once per revolution it's going to send out a single pulse. And that single pulse out of the 1024 of all these other pulses can be used for homing the position of this. Upon initial startup, you have no way of knowing exactly where an encoder is, because the square waves just look symmetrical regardless of your current angle. So instead, if you power up the encoder and then slowly spin it until it hits this pulse, then you know that you're at the same exact position each time. And you can go from there tracking your position relative to that initial coordinate. So the wiring for this one is fairly straightforward. We just have the 3 outputs this time, so digital pin 2, digital pin 3, and digital pin 4, and then the power outputs as well. Overall, this program is pretty much the same as the previous ones. There's a few important changes, but they're kind of beyond the scope of this video, so instead I've written about them in a blog post that I'll link in the description down below. Primarily the issue is that the interrupt pins available on the Arduino are only digital pin 2 and digital pin 3, but because we have a third channel output, we need somehow to get an additional interrupt pin, and that's what this library here handles, and you can find more details about that in the description down below. But essentially, yeah, we're just using this special function to enable the interrupt pins. Because the third channel only puts out 1 pulse per revolution, we can use this as a homing function, and to do that we can just reset the 2 counters. For some purposes you may also want to have a cumulative count, which won't clear after each rotation, so you can count multiple rotations. You'll notice that the check direction function is the same from last time as well, because we still want to figure out what direction we're spinning. And we're just outputting the interesting variables here. So I'll go ahead and upload this and we can see what the output looks like. So here you can see the rotation. Right here, or approximately here, is our initial starting position. Actually, you know what? I'm going to put a piece of tape on the output so that you can see the orientation. So yes, with a little bit of it, obviously the resolution on this is very, very good, so it's hard to get the precise 0 point, but I'm oscillating around it, and if I rotate it by a little bit, and what you're seeing with these sawtooth functions is it's actually capping out at 1024 and bouncing back to 0, because that's where we're resetting the counter after each revolution. So after each time I spin this around, it's going to drop back down. But the overall continuous one, that's the cumulative count of A and the cumulative count of B. And if I spin the opposite direction, you'll see them begin to converge back down towards each other. And now I can just wiggle back and forth. Lastly, let's just see what happens when I remove everything and we just look at the direction. So here, every time that it's 1, we're spinning clockwise, and then every time that we're spinning anti-clockwise, it's -1. And so forth.